Okay. I said 20 till. If you're not back, that's when I was starting again, was 20 till. If you're not back at 20 till, 20 till 11. Okay. So, let's start with butane. Because regardless of the reaction that we're going to do, our first step is always going to be, what are the products? So if I'm going to halogenate, and I'm just going to use X2, I'm going to halogenate butane. How many different products am I going to get? And what are they? 2 products, right. What are they? One and 2 halobutanes are going to be my 2 possible products. So A, B, B, product A, and product B. So there are my 2 possible products. And so now I have 3 different sets of conditions that I can do this. I can do it room temperature and light. I can do room temperature and light for chlorination, room temperature and light for bromination, and I can go greater than 300 degrees Celsius for either one. Because at that point, either one of those is going to give the same product. So I have 3 sets of conditions here to determine which one is the major product. So that's 3 problems, 1 structure, 3 problems. Okay? So how am I going to determine what the major product is? I'm going to use this formula of percent product equals selectivity times number of hydrogens. So for bromination at room temperature, we've got 1700 to 80 to 1. For chlorination at room temperature, we've got 5 to 3.4 to 1. Those are our selectivities, and then the number of hydrogens we can count. So let's do that for each reaction condition. So for product A, let's start with, we're going to do chlorination at room temperature with light. And we always do things at room temperature with light. So for product A, I'm going to use that formula. So how many hydrogens will give me product A? Six. So there's actually going to be 6 hydrogens in each of the molecules. And then for product B, how many hydrogens are there that give product B? 4. So there's 4 hydrogens for each one of those. So we should probably do the simplest one first. What's the simplest one? Which set of conditions? 300 is the simplest one because there the selectivities are all 1. So it's 1 times 6 and 1 times 4, which means I have a 6 to 4 ratio. And so what's the major product when I do this reaction at greater than 100? Greater than 300 degrees Celsius. The major product is A. Because selectivity of 1, because it's forming the selectivity of 1 for everything, primary, secondary, tertiary, all 1, just times the number of hydrogens. So this is the statistical set of problems or products. That's based totally on the number of hydrogens. So I'm going to get a 6-to-4 ratio, or 60%. I'll get 60% of A and 40% of B if I do this reaction with either chlorination or bromination at greater than 300 degrees Celsius. Now that's a limitation. Because let's say you're working at a chemical company and somebody says, hey, can you make me some 1-chlorobutane? And you say, well, I'll do that by free radical halogenation. The best I can do is 60% in that reaction. I can't go any higher. That's it. Pure statistics say 60-40. So if I'm going to stay in business, I need to figure out somebody to sell the other 40% to. Because I can't just throw it down the drain, or I won't be in business very long. Unless I have a government contract, then I can probably stay in business forever. But we can't really throw away 40% of our product. So there is a limitation in free radical halogenation as to how high you can go. If on the other hand somebody said make me 2-bromobutane, and I say I'm going to do it greater than 300 degrees, I'm only going to get 40% yield. I'll be fired. I won't be out of business. I'll just be fired for making the minor product. So that's what we have to do. Put in the selectivities. Okay, now chlorination at room temperature. What kind of... So first of all, there's 2 CH3s over here that give me product A. There are 2 CH2s that give me product B. Point of caution, the numbers of hydrogens always come from the reactant. Because sometimes people will do something else, which I won't even mention. They always come from the reactant. So 6 and 4. All right, for chlorination, what kind of carbocation or what kind of radical am I forming A from? Primary, secondary, tertiary. A is coming from what kind of radical? Primary. What's the selectivity then for primary for chlorination at room temperature? 1. What is it for bromination? 1. What is it for any primary? 1, because that's what we decided to make everything against. It's all relative ratio, 2 chlorine, or 2 primary, which is 1. So it's really the B. So B, what kind of radical is it coming from? The secondary. What's chlorination secondary? It's 3.4. And for bromination, it's 80. So we just multiply the numbers. We got a 6, we got a 6. We've got a 13.6. And then we've got a, what is that? 4 times 80 is 320, right? So what's the major product for chlorination and bromination? Its product B. But notice the percentages would be much different. So how do you get the percentages out of these ratios? You add them up and divide. So in other words, the percentage of chlorination of B would be 13.6 over 19.6 would be its percentage. 13.6 over the 6 plus the 13.6 to give me the total number. But for bromination, it would be 320 out of 326. So it's, by my count, that's greater than 90%. For forming product A. And in each of these cases, product B is the major one. But if I wanted to make A, the best I could make A would be, since it's not the selective product, the best I can do is go pure statistics. And if I go pure statistics, it's only 60%. So, and what this also tells me is that for the bromination, the best I can do is 320 out of 326. I can't get 100%, but I get 90-something%. So that formula is going to give me the number, and the molecule, the product with the highest number, is going to be the major product. But bromination, because of the numbers of 1700 to 80 to 1, what that means is it would take 1700 primary hydrogens to overcome one tertiary hydrogen. In other words, statistics can overwhelm selectivity, but never in bromination. So for instance, let's go back to this one. Chlorination at room temperature, what's the major product? A, B, C, or D? And then you can write your letter or letters if they end up tied on the board. Okay. 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 Any other answers? Okay, so our most popular answer is B, followed by a C and an A. Anybody want to change their answer? No? All right, what would be the numbers for A? Well, just in terms of selectivity times number of hydrogens. 1 times 6 hydrogens? Because A is different than D. You probably had D in with A, right? If you thought D was the same as A's, then you would have 9 A's, which would actually be the major product, but they're not. There's 6 A's, and it's a selectivity of 1 because it's primary. What about B? 5 selectivity times 1 hydrogen. So right now, who's ahead? A. How about C? So secondary 3.4 times 2 hydrogens, which would give me 6.8. So now C's in the lead. And then D, 1 is going to be a selectivity of 1 because it's primary, times 3 hydrogens, which is 3. So who wins? C wins. Just barely. Well, actually, just barely over A. So, what's the point of this problem? That, you know, I wouldn't have said it that way, but I will from now on. The point of this problem is you got to do the math. Because for chlorination, it's possible to have a higher number of hydrogens that will overcome the selectivities. In other words, if it's only 5 to 3.4, 2 hydrogens at 3.4 will beat 1, 5. Now, if I change this up and I said, let's do this reaction with bromination at room temperature, and I said, what's the major product? I don't have to do any math, really, because if there's a tertiary position, that's where it's going. That's where the bromine's going, because it's 1700. If there's no tertiary position, then it's going to go to the secondary position, because that's 80 to 1. So in this case, the major product would be B, would be 1700 times 1H. For B, it would be, no, sorry, that's for B. So 1700 times 1H. For A, it's 6 times 1, or it's 1 times 6. 1 times 6 H's. Then for C, it's now 2 times 80. 2 H's times 80 would normally win, but not with a 1700 in play. And then D would be 3, would be a selectivity of 1 times 3 H's. So in this case, we would have 1700. B would be the major product. So for bromination, put the bromine in the most selective position, tertiary. What if there's 2 tertiary positions and they're not the same? Then equal products. We have 2 major products. What if you have two CH2s I would check to make sure there's not two CH2s that are the same, because that would give you 4 hydrogens versus 2. So you always have to do the math. It's just easier with the bromine. So that's how we determine the major product of the reaction. Okay. So that's free radical halogenation. Really selectivity versus statistics, but you always get a mixture of products. There's no way around that. Okay. Next. The next chapter is dienes. Or actually the next chapter is allylic systems. The next chapter is allylic. That is chapter 19. Allylic systems and dienes. Oh, by the way, if you've not done any Tophat problems from chapter 13 or 14 or 15, you might want to do some. Because I did look back last night at chapter 13. I was going to write the scores down. And there are some zeros, so get those taken care of before the exam, please. Please, either get them done or done. Okay. So I would say the problems by chapter 18 by the exam. Next Monday, I will start writing scores down. Okay, allylic systems. What is an allylic? What does that mean? Here's what it means. Allylic is the carbon next to the double bond, and it has a special position, being next to the double bond. First of all, in terms of free radical halogenation, when we brominate, well, I'm going to take that back. When I want to free radically halogenate, the allylic position, if it's there, is going to be preferentially halogenated. Why? Because if you think about, here is an allylic radical. That's a secondary allylic radical, but it's more stable than your run-of-the-mill secondary allylics. Why? Because I could take this pair of electrons in the double bond and I can split them apart, and I can write a resonance structure where I can move the radical basically to the primary position. So in other words, I can write a resonance structure here by taking the double bond, splitting it up into 2 unpaired electrons, pairing up this unpaired electron with this one, and then moving the other unpaired electron to the outside. The more resonance structures I can draw, the more stable the intermediate. So this would be a very stable radical. So when we free radically halogenate, we're going to free radically halogenate preferentially to the allylic position, and its selectivity is going to be as good or better than a tertiary. Which means that if I said, draw me the major product of that free radical reaction at room temperature and light, what's the product going to look like? Write it down. I want to see it. Okay. What? What do you want to do with the double bond otherwise? Oh. So in theory, if we have if we had two different radicals here, if we had the radical here and here, we could get two different products. But let's go with the one that's the most stable radical. Okay. Okay. I'll come back to that issue. We'll come back to that issue. Okay. Interesting. Now, what's the major product of that reaction? Okay. We're missing one. Okay. 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 No double bond. So what's the difference between these two reactions? The light. So we should ask ourselves then this question. And this is going to be a rhetorical question. So if you want to answer it, feel free, but if not, I will. So which one of these two is faster? The bromine adding to the double bond, or the bromine having to do the free radical halogenation? Oh, nobody's answering. That's because I said I would. It turns out that the bromine will react with the double bond much faster than it'll do free radical halogenation. Now, that's something that you wouldn't know unless, I suppose you could look up the reaction on YouTube, because I'm sure somebody has added red bromine drops to a double bond, and instantly the red color disappears because the reaction occurs. That's actually a test that we can use for a double or a triple bond. Somebody gives you a molecule and says, hey, I think I got a double or a triple bond in here, and you don't have an IR to do a quick screen, or you don't even know what an IR is, then you could add a drop of bromine, and if you added it and it quickly disappeared, it's a double or triple bond. If the red color persists and you have to put it in sunlight to get it to disappear, or a really intense UV light, it's going to be an alkane. So here's the issue. The issue is the major product of this reaction, the major product of the first reaction is that. It's not free radical halogenation. Now, did I expect everybody to write the product that I kind of put you in a position to write? Yes. So here's the issue is we cannot do free radical halogenation on a molecule with the double bond. So we need a new reagent. And so the new reagent that you'll see instead of light bromine, that's only going to be this set of this reagents are only going to be used for alkanes. if you have an alkene and you want to do free radical halogenation, number one, you get rid of the bromine and you put in a molecule called NBS. That stands for N-bromosuccinimide. So this is succinimide with a bromine attached to the nitrogen. So this is N-bromosuccinimide. That's NBS. So if you want to do free radical halogenation on a double bond containing molecule, you've got to use NBS. Where will it halogenate? It will halogenate like 1700 to 1 at the allylic position. You have no choice. Bless you. So we normally wouldn't have to deal with that when we were just talking about alkanes, but now we know about double bonds, and so we have to change our reagent. So the NBS has to be used. Now NBS can be used to halogenate an alkane as well, but I'll just use bromine and light, or bromine and heat, or chlorine and light, chlorine and heat to do that. But when we change to an alkane, we're going to brominate at the allylic position, but we have to use NBS. Now, and the mechanism of this, basically NBS, when you heat it, it produces a Br dot. But it never produces Br2, because Br2 would add to the double bond. So NBS specifically eliminates the bromine addition to the alkene. So today we talked about mechanism of free radical halogenation, how you determine the possible products, and then the major product depending on whether it's bromination, chlorination, etc. In the folder for today, you'll see a practice problem on writing the mechanism. You'll see a whole series of problems where I've said add X to this, write the possible products, and then tell me what the major product is, if it's chlorination, room temperature, bromination, room temperature, or greater than 300 degrees. So you can get practice on those before next week. I think I said that I was going to give you a take-home practice problem on writing the mechanism. I didn't forget. So use cyclohexane and so you're going to put a bromine onto the carbon of the cyclohexane, and so that's going to be the take-home quiz problem for tomorrow. All 6 steps. I want you to write the complete mechanism for that. Initiation, 2 propagations, 3 terminations. And there's what we did, there's what's in the book, and there's also an additional practice problem on there with the narrated answer key if you want to practice it before this. Cameron? Yes, I do want transition states for this. So we want all the steps, all the transition states. Exactly like we did it at the beginning of class. Well, exactly like I did it at the beginning of class. Okay. I put the exam key, the exam answer key in yesterday's folder. It's at the top. Take a look at these. If you have any questions, email me or come and see me. I did also clean up the gradebook by removing stuff that's extraneous and setting up the percentages along with the syllabus percentages for the grades. This is just the first of 4 exams. There's still 3. This is the first of 3 regular season exams and then the final exam. So you still have 2 more of these to go. The final is its own beast. We'll get there. Don't worry about it now. Okay? All right?